So, previously we saw that the slope of a tangent line could be found by examining the slopes of the secant lines as the second point approaches the point of tangency. The slope of the tangent line was the limit of the slopes of the secant lines. But now we're going to see an algebraic way that we can find the slope of a tangent without using the table of values and guessing. So if a curve has an equation y equals f at x and the tangent point through point P, which is a comma f at a, is desired, then the slope of the tangent line can be found using this limit formula. The limit as x approaches a of f at x, so that's the original function, minus f at a, so it's the value of the function when x actually equals a, and notice that's on top. So if a is a non-permissive value, that's fine, right? Doesn't matter. Over x minus a. So if we evaluate this limit, it'll give us the slope of the tangent. So let's say we wanted to find the equation of the tangent lines, and the first step will be to find the slope, and then you can use the point and point slope, or y equals mx plus b, to determine the actual equation. But first we have to find the slope. So we want to find the equation of the tangent line to the given curves at the given point. So the first one is y equals x squared. So again, m, which is the slope of the tangent, can be found by taking the limit as x approaches a of f at x, which is x squared, minus f at a, which we're already given. That is the y value at the point of tangency. That's the answer you'll get for y when you let x equal 2 in the equation, over x minus a, or x minus 2. And I should have put, instead of a in there, I should have put x approaches 2. Because that is our a value. It is the value of x at the point of tangency. So right now, 2 is a non-permissive value, but as we've seen, we can evaluate this limit by getting rid of that denominator of x minus 2. And we can do that by factoring. The top is a difference of squares. So it's x plus 2, x minus 2. And so the x minus 2's cancel. And we can now evaluate this limit when x equals 2. 2 plus 2 is 4. So that's the slope of the tangent. And now we can find the equation of the tangent line, and we can either use y equals mx plus b, or we can use point slope. It doesn't matter. So all equations, well, most equations have an x and a y in them. So that's why we have a y and an x in the equation. x1 and y1 would correspond to the point of tangency, and m is the slope. So technically that is the equation of the line in point slope form. That is the equation. Normally, we write it in slope intercept form by multiplying out the brackets. And in this case, we would add 4 to both sides. And there's the equation. When we find the slope of the tangent using this formula, and then in a few minutes we'll see a second formula that can also be used, a little bit different. These are called finding the slope of the tangent using first principles. Next chapter, we're going to get into something called derivatives, and we're going to see how we can use derivatives to find the slope of the tangent. Okay? But we start with first principles. So for number 2, we want to find the equation of the tangent line to the curve y equals 2x squared plus 4x minus 1 at the point 2, 15. So again, we start by finding the slope of the tangent. It'll be the limit as x approaches 2 of f at x, which is 2x squared plus 4x minus 1 minus f at 2, which we already know is 15 because we're given the y value when x equals 2, all over, again, x minus 2. So when you simplify the top, you're going to get minus 16. And then once again, 2 is a non-permissive value, so we need to do something to get rid of that x minus 2 on the bottom. And again, that something would be factoring. First, you can take out a common factor of 2, and then the quadratic that you're left with can be factored. It would be x plus 4, x minus 2, and now the x minus 2's would cancel. And you can now evaluate that limit. When x is 2, you're going to have 2 times 6, which is 12. So that is the slope of the tangent. And we can find the equation of the tangent line in the last example. I used point slope. We can also do it using y equals mx plus b. And we start by first finding the value of b by plugging in x and y that come from the point of tangency, which again is 2, 15. So y is 15 when m, the slope, is 12, and x, the x value at the point of tangency, is 2. So we can use this to find out what the b value is. So 15 will equal 24 plus b. b then would be negative 9. And the equation in slope-intercept form then would be y equals 12x minus 9. That's in slope-intercept form. If you were asked to write it in general form, remember that's where you have everything on one side equal to 0 on the other. No fractions or decimals. And normally the first term, the x term, is positive, which means we would bring the y over with the 12x and the 9. And there's the equation in general or standard form. Okay, so again, we're finding the slope of the tangent using something known as first principles. So the third example, what I would first do is get y by itself. That's fairly normal. So this is a rational function. And if we want to find the slope of the tangent, we would find the limit, in this case as x approaches negative 2, of f at x, which is 1 over x, minus f at a, which is negative a half, over x minus negative 2, which becomes x plus 2. So again, negative 2 is a non-permissive value, so we need to do something here. First, the minus minus becomes a plus positive on top. And then we're going to get rid of the denominators in the numerator by multiplying all the terms by the common denominator of 2x. Can't forget to do the bottom as well. So the x's cancel, the 2's cancel. We've gotten rid of the denominators in the numerator. So we're left with the limit as x approaches negative 2 of 2 plus x, which is the same thing as x plus 2. So they would cancel. And you're left with 1 over 2x. So we can now evaluate this limit. When x equals -2, you're going to have 1 over -4, or -1/4. So that is the slope of the tangent line. And now we can find the equation. So again, if I use point slope, doesn't matter which one I use. I could also use y equals mx plus b. I'll have y minus -1/2 equals m, which is -1/4, bracket x minus x1, which is -2. Again, the minuses become plus positive. So I'll get y plus 1/2 equaling -1/4 x minus 1/2 when you multiply the -1/4 by the +2. And then to get y by itself, I'd subtract that 1/2 from both sides. And if you have -1/2 already and you subtract another half, you're going to get -1. There's the equation in slope-intercept form. In general form, we would first get rid of the denominator by multiplying all three terms by 4. And then I'd bring the x and the 4 over. Remember, in general form, the x term should be positive. So it'd be a positive x, a positive 4y, and a positive 4. So there's the equation in general form. Right, so for number 4, we want to find the equation of the tangent line to the curve of y equals the root of x minus 2 at the point 6, 2. And once again, we can find m, the slope, by taking the value of the limit as x approaches a, which in this case is 6, of f at x, which is the root of x minus 2, minus f at 6, which is 2, because we're given the y value at the point of tangency to be 2. That's the value of y when x equals 6, all over x minus 6. So again, 6 is non-permissive. So we need to do something to get rid of that x minus 6, and that something would be multiply top and bottom by the conjugate. So on top, when we multiply out the conjugate, the front terms, root of x minus 2 times the root of x minus 2 is x minus 2. The outer and inner products will cancel. The last terms, -2 times 2 is -4. And we don't want to multiply out the denominator because we're trying to get rid of that x minus 6, which we will because that's what the top becomes when you simplify. -2 take away 4 is -6. So you have an x minus 6 on top. It'll cancel with the x minus 6 on the bottom. So now we can evaluate the limit as x approaches 6 of 1 over the root of x minus 2 plus 2. It'll be 1 over, when x is 6, 6 minus 2 is 4. The root of that is 2 plus 2 gives us a slope of positive 1/4. And if I use y equals mx plus b, doesn't matter. We can also use point slope. But doing it this way, I need to find b, which represents, remember, the y-intercept of the graph. I need to find that first. Using the point of tangency as x and y, and m is the slope. So y is 2, and the slope is 1/4, and x is 6. So 2 will equal 6/4, which is 3/2 plus b. So when you subtract the 3/2 and you subtract 1.5 from 2, you're going to get 1/2 on the left. That's our b value. So in slope-intercept form, our equation would be 1/4 x plus 1/2. In general form, again, we need to get rid of the denominators. So we'd multiply all three terms by the common denominator, which would be 4. And then bring the 4y over. And there's the equation in general form. Okay? As I said, there's an actual second equation that you could use to find the slope of the tangent line at the point a comma f at a. What's different about this one is the limit is always approaching a value of 0. It says the limit as h approaches 0 of f at a plus h. So remember, a represents the x value at the point of tangency. And then it's going to be plus h. That's a variable that's going to be part of this equation. Minus f at a, which is the same as the previous equation. But then it's all over h. And once again, because h is approaching 0, you can't evaluate the limit by substitution. Can't have 0 on the bottom. So again, we'll have to do some algebraic work to get rid of the factor of h on the bottom. So, same equations that we just did. And we just want to use this first principles formula to find the slope of the tangent. Because it's the same equation, the same point of tangency, so our equations will be the same in the end. So we just need to show that this also works to find the slope of the tangent. So, for x squared at 2 comma 4, again, using that formula above, m, the slope of the tangent, will be the limit as h approaches 0 of f at a plus h. In this case here, a is 2, so it's f at 2 plus h. Wherever we see the variable x in the equation, we're going to replace it with 2 plus h. In the equation, the x is squared, so now the 2 plus h will be squared as well. Minus f at a, which is 4. That's the value of y when x equals 2 in the equation, all over h. Again, 0 is a non-permissive value, so we need to do some algebraic work to get rid of that factor of h on the bottom. Now you could, on top, you could square out the 2 plus h, simplify it, and then factor that quadratic, or you can just go straight to difference of squares, which is what we've done in the past. That's a difference of squares, so it'll be 2 plus h plus 2, 2 plus h minus 2. Difference of squares. So that second factor on top, the 2's will cancel. Right? 2 minus 2 cancels, so you're just left with a factor of h, and that will cancel with the h on the bottom. So now we will have the limit as h approaches 0 of h plus 4, because that's all we have left on top, which is 4 when h is 0. So that's the same slope that we got when we did it using that first limit formula. Same formula, or same slope, I should say. All right. So number 2, we did this equation already. We go back. We found that in this case, the slope of our tangent was positive 12. So we should get the same answer using first principles in the second equation. Should get an answer for a positive 12. And the slope will be the limit as h approaches 0 of f at a plus h. Wherever we see the x, we'll replace it with 2 plus h. So this is going to take a bit more work than the first way we did it. So that just represents the f at a plus h part. And then you got to go minus f at a, which is 15, all over h. And so in this case, I would simplify the numerator. I would square the 2 plus h. Whenever you square a binomial, you square the first term, multiply the 2 terms together and double, square the last term, and then multiply the 2 plus h by 4. That will be 8 plus 4h minus 16. So continuing to simplify on top, multiply out those brackets. So if you look at all the constant terms on top, you've got a positive 8, a second positive 8, which is 16, and then you have a minus 16. So those will cancel. You get rid of the constant term. And that needs to happen so that we can get rid of the h on the bottom, because now we can take out a common factor on top. A common factor of 2h, which leaves us with h plus 4. And now the h's will cancel. Oh, I'm sorry. I didn't add the 8h and the 4h together. That gives us 12h. Okay, so this would actually be h plus 12. Sorry, 6. Because we took out a common factor of 2. That's better. And so now, when you let h equal 0, you're going to have 2 times 0 plus 6. And 2 times 6 is 12, which is the same slope we got using that first limit formula. Okay? Same slope. We did this one before, and we got a slope of negative 1/4 when we used first principles. So we should get the same thing using this limit formula. But like we did before, we need to first get y by itself in the equation. And so again, h is always approaching 0 using this formula. And the first part is f at a plus h. So you're going to replace the x with negative 2 plus h minus f at a, which is negative 1/2, all over h. So if I just simplify or rewrite this a little bit before I start the next part, negative 2 plus h is the same as h minus 2. The minus becomes a plus positive. That's what it'll look like. And like we did before, we want to get rid of the denominators in the numerator by multiplying everything by the common denominator, which would be 2 bracket h minus 2. 2 bracket h minus 2. 2 times h minus 2. And so the h minus 2 will cancel in the first term on top. The 2's cancel in the second term on top. We've now gotten rid of the denominators in the numerator. So you're left with 2 times 1, which is 2, plus h minus 2, and on top, 2 minus 2 cancels, and so you're left with a factor of h on top, which will cancel with the h on the bottom, and we've gotten rid of our non-permissive value. So this will equal the limit as h approaches 0 of 1 over h 2 bracket h minus 2, which we can now evaluate. We got rid of our factor of h on the bottom. So now when h equals 0, 0 minus 2 is negative 2, times the 2 on front gives us negative 4. We get the same slope of negative 1/4. And for the last one, when we did this equation the first time around, we got a slope of positive 1/4. So we should get the same thing now using the second limit formula. So it's f at a plus h. So our a value here is 6. So you're going to replace the x with 6 plus h under the radical, minus f at a, which is 2, all over 0. So if I simplify inside the radical, it'll be h plus 4. Whoops, that should have been an h. And we need to get rid of that factor of h on the bottom. Once again, we would multiply top and bottom by the conjugate. So on top, when I multiply out, the root h plus 4 times root h plus 4 will give us h plus 4. The outer and inner products cancel, and the last negative 2 times 2 is negative 4. So on top, 4 minus 4 cancels. And we have just h on top, which will cancel with the h on the bottom, and we're left with 1 on top. So now we can evaluate this limit. The limit of h approaches 0 of 1 over the root of h plus 4 plus 2. When h equals 0, under the radical you have 0 plus the root of 0 plus 4. The root of 4 is 2, plus the other 2 on the bottom gives us our slope of 1/4. Okay, so both formulas work. There are some cases where one formula might be easier than the other, a little less work involved in some cases, but they both work. So now we no longer have to use a table of values to guess what the slope of the tangent line is. And again, when we get into the next chapter on derivatives, we'll see another way to find the slope of the tangent. And we're going to see as we go through this course that it has lots of uses. Derivatives have lots of uses. Things that you did before in your high school math, you can use derivatives to make it a lot easier. Okay? All right. So you can work on. Yeah. Well, once we get into derivatives, you won't have to use that anymore. But if you are tested on it, which you will be for the first chapter test, you'll be given the first principle formulas. So you won't have to memorize them. So on page 35, you should be working on question 1, all of that, and then 7a and b. I will post these solutions to Google Classroom so you can check your work. Okay?